The supertanker is enormous. Its mass is so large that even a small acceleration requires a huge net force. But when two tugboats pull at angles, some components cancel sideways, and only the forward components help produce acceleration. In this video, we will uncover how Newton's second law turns a complicated looking towing situation into a clean component problem. In the previous lesson, we studied equilibrium problems. In equilibrium, acceleration is zero, so the net force in each direction is also zero. Now we move to non-equilibrium applications. An object is not in equilibrium when it is accelerating. This means the net force is not zero. Instead, the net force equals mass times the acceleration. In two dimensions, we apply Newton's second law separately in each direction. In the x direction, the net force in x equals mass times the x component of the acceleration, and in the y direction, the net force in y equals mass times the y component of the acceleration. The key difference from equilibrium is that the right side of the equation may not be zero. If the object accelerates in a direction, then the net force in that direction must be non-zero. However, it is possible for an object to accelerate in one direction while still having zero acceleration in another direction. That is exactly what happens in the supertanker example. In this example, a supertanker is being towed by two tugboats. The mass of the supertanker is 1.5 times 10 to the power 8 kilograms, and this is an extremely large mass. So even a small acceleration will require a very large net force. The tugboats pull with tension T1 and T2. Each towing cable make an angle of 30 degrees with respect to the tanker's axis. The tanker's engine also produces a forward driving force D, and the magnitude of this drive force is 75 times 10 to the power 3 newtons. The water applies an opposing force, which is denoted from R, and the magnitude of this resistance force is 40 times 10 to the power 3 newtons. The tanker moves forward with an acceleration of 2 times 10 to the power negative 3 meters per second squared. The acceleration points along the tanker's axis, which we call the x-axis. Our goal is to find the magnitude of the two towing tensions, T1 and T2. Before solving, notice the symmetry in the problem. The two tugboats pull at equal angles above and below the tanker's axis. Because the situation is symmetric, we should expect the two tensions magnitude to be equal. But we should still prove that using Newton's law rather than simply assuming it. Now we draw the force diagram for the tanker. The tanker experiences two tension forces from the towing cables. T1 pulls forward and upward at 30 degrees above the tanker's axis. T2 pulls forward and downward at 30 degrees below the tanker's axis. The drive force D from the tanker's engines points forward, and that is along the positive x direction. The water resistance force R opposes the motion, so it points backward in the negative x direction. The acceleration is along the x-axis, and this tells us that the y component of the acceleration is 0. This is a very useful structure. The y direction behaves like an equilibrium condition, while the x direction is a non-equilibrium condition. So the free body diagram would look like this, and you have a dot to indicate the tanker, and the forces are drawn here. So we have T1, T2, D, and R. Now let us organize the force components. Because each cable angle is measured from the tanker's axis, which is the x-axis, the x component of each tension uses cosine. For T1, The x component is positive t1 cosine 30 degrees because it points forward. The y component of t1 is positive t1 sine 30 degrees because it points upward. For t2, the x component is positive t2 cosine 30 degrees because it also points forward, and the y component of t2 is negative t2 sine 30 degrees because it points downward. The drive force D points entirely in the x direction, so its x component is positive D and its y component is 0. The resistance force R points backward, so its x component is negative R and its y component is 0. Now we can already see the physical meaning of the components. The vertical tension components oppose each other. The forward tension components work together. This is why angled pulls are less efficient than straight pulls for producing forward acceleration. Only the x component contributes to the forward acceleration. With the components identified, we can write Newton's second law in the y direction and x direction. So the net force in x direction is equals to positive t1 cosine 30 degrees plus t2 cosine 30 degrees plus d minus r, and this is equals to mass times acceleration in x direction. And we can also write F net y, which is equals to positive t1 sine 30 degrees minus t2 sine 30 degrees plus 0, and that is equals to mass times acceleration in y direction, and this acceleration in y direction is also equals to 0. Now we have two equations and two unknowns to solve for. We need to find t1 and t2. So let's start by the second equation. We can bring this t2 sine 30 to the other side of the equation, so this will become t1 sine 30 degrees equals t2 sine 30 degrees. From here, you can clearly see the sine 30 degrees cancels out and we get t1 is equals to t2. Now we can use this in our first equation and solve for t1. Now we can rearrange this. So 2 times t1 cosine 30 degrees plus d minus r equals max, and then 2 t1 cosine 30 degrees is equals to max plus r minus d. So from here we get t1 is equals to max plus r minus d divided by 2 times cosine 30 degrees. Now we can substitute the values to this equation. So the mass is 1.5 times 10 to the power 8 kilograms, and that is multiplied with the acceleration in x direction, which is 2 times 10 to the power minus 3 meters per second, and then we have to add the opposing force, which is 40 times 10 to the power 3 newtons, and then minus the driving force 75 times 10 to the power 3 newtons, and then this whole thing divided by 2 times cosine 30 degrees. So this is equals to 1.53 times 10 to the power 5 newtons. So we can write T1 equals T2 equals the tension, which is 1.53 times 10 to the power 5 newtons.